Okay, good morning, everyone. So we're going to talk more about complex numbers today, and so I thought I'd start off with the question that Huang raised last time. He said, "Is there a connection between the complex numbers and matrices?" And I kind of forgot about it, but so let's recall what we're doing. Talking about complex numbers as another one of these things called fields. Hey, Huang. Another example of field, and the other thing we'll talk about today is Euclidean spaces. Euclidean spaces are examples of things that are called metric spaces that we'll need later. Okay. And R and C are also examples of metric spaces. In any case, so remember what we're doing. We have the complex numbers, and we started off with basically pairs of numbers in R2, right? So we're on the plane, right? Pairs of numbers AB in R2, and then we change this into a field by defining an addition and a multiplication on it, right? And Huang asked, is the multiplication related to matrix multiplication? And it is. So, great observation. I give you plus 2 on the next exam. Plus 2 percentage points. So yeah, the exam maybe only like 30 points. So.
I'm a senior, so I don't care that much.
What?
I'm a senior, so I just want to study, right?
You just want to learn, right?
Yeah, I don't care that much.
You don't care. Okay, even better. But in any case, I give you plus 2 on the next exam. Okay, so so here's what you do actually. So you take C. So here's C. And you can embed it in the matrices, the 2x2 matrices. Okay. What you do is you take your A plus BI, and then you embed it into the matrices as a matrix like this: A, B, 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 A. Okay. So then, clearly when you add things, right, then that corresponds to adding the matrices, right? But what's more interesting is the matrix multiplication corresponds exactly to the complex multiplication over here. So if we take, for example, two numbers, A plus BI times C plus DI over here, and we look at the corresponding A minus B, B times A, C minus D, D times AC, and we multiply that out, right? You get AC, AC minus BD. Down here you also get AC minus BD, right? And here you get BC plus AD, so AD plus BD, AD plus BC, and you get negative AD minus BC. Okay, right? And that's good because when you multiply these guys, what do you get? You get AC minus BD, comma, right? And then the complex guys are going to be BC plus AD, so AD plus BC here, right? So, right, and as you see, this is what you get, when you take this and then map it, embed it in when you take this guy and embed it in the matrices, you get this number, right? So that is, you can multiply them and then embed, or you could embed them and then multiply. And either way, you're going to get the same thing, right? So this map preserves the field operations, right? So it basically isomorphically embeds C into the matrices. Okay, so that's nice. Okay, so really cool question, another cool thing to notice is that if you look at this A minus B, B, A, right, and we rewrite it as, so thinking of this, the vector here, A, B, well, the norm of the vector, the magnitude of the vector is going to be A squared plus B squared, right? The square root of A squared plus B squared, right? So what you can do is you can pull out that norm, pull out the norm, right? So you get A over this thing minus B over this thing, B over the square root, A over the square root, right? Right. And so what that gives you then is you get this this thing. If you think about, let's see. So the determinant of this is going to be what?
1.
1, right? It's going to be 1, right? A squared plus b squared, a squared plus b squared, right? A squared plus b squared, a squared plus b squared, right? The determinant of this is 1, right? In other words, if I think of this as a negative b, a, right? This times this minus this times this, yeah, capital A squared plus b squared is equal to 1, right? So, right. So in other words, this A and B are on the unit circle, right? This A and B are on the unit circle, right? Their coordinates A and B on some unit circle, right? And in other words, these can be thought of as, you know, cosine and sine of some angle, right? So you can rewrite this as, you know, some scaling number r, which is the norm of the vector, times, you know, cosine theta, negative sine theta, cosine theta. Okay. Does anybody know what this sort of thing is from linear algebra? Do you guys see this in linear algebra?
I sense rotation matrix.
It's a rotation matrix, right? This is a rotation matrix of angle theta. So when you apply it to, you know, to a vector, it rotates it by that angle, right? It rotates it by that angle, right? And so this is another way of seeing what I said last time, that when you multiply complex numbers, what happens is that you get a rotation and then a scaling, right? You rotate, right? If you take one complex number, right? I have this complex number here, z, say, and I multiply it by some other complex number, you know, this one, right? What will happen to it, it'll be rotated by some angle, right? Rotated by some angle, and then scaled by some factor, right? Multiplied by r. Multiplied by r. Okay. So, right, this is a very clean way of saying that, sort of clarifying that comment that I made last time, that when you have two complex numbers, you know, z and w, and you multiply them, then what you do is you take, you know, this triangle, and then you create a similar triangle. So this is the unit circle. You create the similar triangle, and then this point is zw, right? In other words, you know, that's exactly what we're doing. We're rotating it by this angle, right? We're taking this guy, we're rotating it by that angle, and then we're scaling it by the scaling factor. Okay. And just to give you some, you don't worry if this isn't, you know, absolutely clear on first viewing, but I hope this gives you some idea of the geometry of the complex numbers. Okay. Okay. So that was all in response to Huang's comment. Okay. So let's see. Where are we? Right. Okay. So now back to sort of like some more sort of. I mean, not so exciting stuff, but it's important. Okay. 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 I'm gonna hold off on saying something else. I was gonna add more, but let me not do that. Okay. So okay. Back to so there is this sort of you know, alternate way of looking at the complex numbers as matrices. But let me just let's just not think about that for right now and just think about that we are dealing with points on the plane. Okay. Okay. So some terminology. So we have this point z. So complex numbers usually use, people use x and y and z for real numbers. People use w and z and Greek letters like zeta, etc. for complex numbers. Okay. So suppose we have this complex number. By this, we mean the first coordinate. This is the real, what's called the real part, right? If you think of this thing as a plus bi, right? It's just the a, right? The real part of the number, right? We write this for b being the imaginary part of the number. Okay, so it's just notation. Really important. When we write z bar, what we mean is a minus b. Okay, in other words, a plus a minus bi. In other words, when you take you have some point here, and you take its reflection across the real axis, right? And that thing is called the complex conjugate. Okay, complex conjugate. Complex conjugate. Okay, so okay, so some properties of complex conjugation. First off, the conjugate of the sum equals, well, what do you think it would be? If you take two things and add them, two vectors and two numbers and add them together, and then take the complex conjugate, it'll be the same thing as
The sum of the conjugates.
the sum of the conjugates. Right? So you can see that sort of geometrically, right? Because you know that if you take one vector, right, and then you add on to it another vector, right, and then you reflect it, that's the same thing as if you took the reflections and then added them together, right? So geometrically it's obvious. Algebraically you can just work it out. It's also obvious. Similarly, if you take two numbers and multiply them, and then take their complex conjugate, right? So you take, you've got one number, you've got the other number, you create the similar triangle, right? And you take the complex conjugate. Again, sort of geometrically, you can see that it's going to happen the same way, right? If you took the complex conjugates, right, and then created the corresponding similar triangle, you're going to get the conjugate of the product of the conjugates. Right, and again, you can see that algebraically just by calculating it out if you want. Okay. Another one. What happens when you add the number plus its conjugate? What do you get then? You get a real number. What real number? Twice the real part of the twice the real part of the number, right? Right, because when you add this guy and this guy, right, you're going to get twice the real part. You get a real number, it's twice the real part. And similarly, right, when you subtract z, when you have z minus its conjugate, well, you're going to get twice I times the imaginary part. Final observation is that z times z bar is a real positive number, except when z is 0. Right. Right. Of course, when you take a plus bi and multiply it by a minus bi, you end up with a squared plus b squared. Right, so, right, the cross terms will cancel, and then you get negative I squared times b squared. Right? I squared is -1, and so you get b squared. Okay. Good. Everyone okay? Okay. That leads us to the definition of the absolute value, basically. So whenever you have any complex number, you define the modulus. So when people talk about the absolute values of complex numbers, they call it the modulus, but I just call it the absolute value. But you'll see both terms. Okay, so the modulus is just, of course, what you would think it is. It's the square root of z times z bar, right? Z times z bar. So this corresponds to your normal notion of Euclidean length, right? If you're in R2 and you have this point x comma y, the magnitude is the square root of x squared plus y squared, right? And that's all we're doing here. Okay, so it's the same thing. Okay, but you just write it. You can write it as z times z bar to the 1/2. So notice that. So remember when we were talking. So just to sort of a callback. When we talked about 1 over z, we said that 1 over z, 1 over a plus bi was a over a squared plus y squared plus b over a squared plus b squared times I. Right? And now, so minus. Yeah. And now maybe you see what that actually is. That is a minus bi times 1 over a squared plus b squared, right? Which is the complex conjugate divided by the modulus squared, right? So this is your z. This is the multiplicative inverse of z, and that makes sense because when you take z times this, right? What do you get? When you take z times this guy, what do you get? Well, you get z times z bar, which is just the modulus squared over the modulus squared, right? And so you get that. Okay. So earlier we just sort of pulled it out of the hat, like the multiplicative inverse is this thing, but actually you want to remember it's just z bar over the modulus squared. Okay. This is the real way of thinking about it. Okay. Okay. Yeah. Okay. Which corresponds, just for fun, if you think about the matrix, this corresponds to the matrix 1 over a squared plus b squared, a, b, negative b, a, right? Which is the matrix inverse of the original matrix. Okay, so as it should be, because multiplication corresponds. Okay. Okay, so complex conjugate, seemingly trivial, but actually a useful tool. Some properties of the modulus that maybe are obvious to you, but yeah, but these will be useful. So a lot of analysis is talking about the sizes of things, right? Trying to control the sizes of things. To analyze something means to break it into pieces, right? Literally, analysis is the opposite of synthesis, right? You break something into pieces. Synthesis, you make something out of pieces, right? And a lot of analysis involves taking something that you're trying to control and then breaking it into small pieces and then establishing control over those small pieces, okay? And when we're talking about control, often we're talking about control over the size, okay? So we have some properties about size that that will be useful to us. Okay, so here they are. First, that this is sort of obvious, but that the modulus is always positive, right? As long as you're not the zero, right? Second, the modulus of z is the same thing as, what am I going to write here? The modulus of z conjugate is the same thing as the modulus of z, right? That's obvious, right? It's just a reflection. Third, that the modulus of z times w is the same thing as the modulus of z times the modulus of w. Okay. Fourth, that the modulus of the real part, the absolute value, maybe I should say, of the real part is less than or equal to the modulus of the entire complex number. And the last one, maybe the most important one, is that the modulus of the sum, what am I going to say? Anybody know the answer to this? The modulus of the sum, the absolute value of the sum, something.
Less than or equal to.
Less than or equal to
Or equal to.
the sum of the absolute values, right? This is the so-called triangle inequality, right? Triangle inequality. And maybe Huang, don't shout out, don't raise your hand.
Oh.
Raise your hand before answering, okay, so that other people can also answer. Yeah. Okay. Triangle inequality, right? You can see why that is, right? Why it's called the triangle inequality, right? You've got 1 point, you've got 1 point z, you got 1 point w, right? You add them together, and you get this point here, z plus w. Right. And so what it's saying is that the size of z plus w is controlled by the sum of the sizes of z and w. Right. So this length here is z. If we're thinking of these guys as vectors, as we could, as real vectors, right? This is the magnitude of this vector. This is the magnitude of this vector. Right. This is the magnitude of the sum vector. Right. This guy is the length of one side of a triangle is controlled by the sum of the lengths of the other two sides. Right. That's why it's called the triangle inequality. This is we often introduce this in calculus, right? It's just, of course, for real numbers, it's also true. But the trouble is you can't really see the triangle inequality because you're on the real line, right? It's a flat triangle, right? It's a degenerate triangle. But once you're in 2 dimensions, you can actually see it. So yeah, triangle inequality seems really trivial, but it's actually one of the most commonly used tools in analysis. Because you take your thing, and then you say, oh, whatever I'm looking at, I can break it up into the sum of two smaller things, and then the size of that thing is controlled by the sum of the sizes. So if I can control the sizes of those smaller things, I can control the size of the original thing, right? If I know that each of these things is smaller than 5, I know the original thing is smaller than 10. Right. Okay. So I always comment at this point that I have a friend who says that the triangle inequality is the inequality that he hates the most in all of analysis. Because to him, it's defeatist. You've sort of given up on trying to, you've given up on trying to find the actual size, right? Once you make this move, you say, I'm not gonna try to get this thing anymore. I'm gonna try and get the sums of these sizes. So I've given up on actually trying to find the actual size. I'd say all of his, well, I don't know all of his, but much of his work has been finding the actual size of things, using a much hated technique called the Bellman function technique. But anyway, okay. So let me see, which ones should I talk about? I'll talk about. Let me talk about C first. Why is it true that the modulus of the sum equals the product of the modulus of the product equals the product of the moduli? First you just do a calculation, and you see that this thing squared equals this thing squared times this thing squared. Okay, and then you say, well. So this and this have the same square. Okay. And then we pull out the theorem that we did last time that there's only one positive square root for each number, right? So these are positive reals, right? Both positive reals, both positive real numbers, and they're both the square root of the same number, right? They're both the square root of the same number, and so they must be equal by the uniqueness of square roots, right? So we need to use uniqueness of square roots, or really roots, right, that we showed last time. Okay. So I just wanted to point out that in D, showing that the size of the real part is smaller than the size of the original size of the real thing, the original thing. Sorry. Say, well, look, if Z equals A plus BI, then the absolute value of the real part is, of course, the absolute value of A, which is the square root of A squared, which is less than or equal to the square root of A squared plus B squared, which is the modulus of Z. Okay, so right, we're trying to show that this thing is smaller than this thing, right? And so you say, well, what is this thing? This thing is just this. This thing is this, right? And so right, the square root of this thing is going to be bigger than or equal to the square root of this thing. Okay, so just an example. I think the most interesting one is this last one. Okay, so we want to show that we want to show that that this number is less than or equal to this number, and we use so what we do is we show that the square of one is less than or equal to the square of the other. Okay, so we're using a fact that if you're dealing with if you're dealing with real numbers, like real positive numbers, so if A and B are both positive numbers, then A being less than B is equivalent to being A squared being less than B squared. Okay, right, so if A is less than B, sorry to do this, but if A is less than B, but then A squared is less than B squared, right? And if A squared is less than B squared, then A is less than B. Okay, so let's just take this as a fact for now. Maybe I should prove this, but let's just, so what the point is that if you want to show that, if you're dealing with positive numbers and you want to show that one is less than the other, it suffices to show, it's equivalent to show that the squares also satisfy the same relation. Okay, so when we come over here and we want to show this, it actually turns out to be easier to show that the squares satisfy the same relation. Okay, so let me, I'm going to do that. Okay, so let me do that over here. Okay, so this thing here, the square of the sum of the square of the moduli of the sum equals is the same thing as z plus w times the conjugate. Right. That's what that is. Right. And I can I can separate this. Right. This is just the sum of the conjugates. The conjugate of the sum is the sum of the conjugates. Right. So let's work that out. What is that? That's z bar plus w z bar plus z w bar plus w w bar. Right. Okay. Well, z bar is just modulus squared, right? W bar is also modulus squared, right? And then we have these things. You have w times z plus z times w, right? But you see that what's the conjugate? So wz bar conjugate is w conjugate z conjugate. Right? Right? But z conjugate means you flip it and then you flip it back, right? So that's just z, right? That's just w bar z, right? So w bar, which is this thing here. So these guys are conjugates to each other, right? And so when you add them together, you get twice the real part, right? So this is equals twice the real part of z w conjugate. Yes? Okay, right. But we just showed in part D that the size, so this is going to be smaller than this. Right? Whenever you take, if you have a real number and you take its absolute value, it just gets bigger or it stays the same. Right? And then we use part D and say, well, this is smaller than equal to this plus twice this plus this. Right? But that's the same thing. That's the same thing as z conjugate, z modulus of z plus modulus of w squared. Right? Because this is just the product of the moduli. Right? So I get z squared, modulus of z squared plus twice product of the moduli plus modulus of w squared, which is just this thing squared. Okay, so we got it, right? this thing is controlled by this thing. So that gives us the triangle inequality. Okay, everybody okay? Any questions? Charlotte, you look like you might have a question.
No, I think I got it.
Okay. I'm phenomenally bad at reading people's expressions, but I will try every once in a while. Like my daughter just said to me the other day, Dad should learn how to tell the difference between when your kids are mad and when your kids are sad. I can't tell them, right? When they're mad or they're sad. I'm like, don't get angry at me. I'm not mad, I'm sad. Okay, sorry. Okay. Yeah. I joke that it's because I have few facial expressions myself, so I can't read other people's facial expressions. Okay. Okay. Next important thing, Cauchy-Schwartz inequality. Cauchy-Schwartz inequality. Okay. How many of you heard of the Cauchy-Schwartz inequality? Okay, great. Somebody tell me what's the Cauchy-Schwartz inequality from your previous knowledge. What did the Cauchy-Schwartz inequality tell you? Where did you see it?
Linear algebra.
Linear algebra. Okay. Right, and you saw it with regards to dot products, probably.
Mm-hmm.
Right. So I don't know. You're all looking kind of shy. So let me just write it up. Cauchy-Schwartz inequality says this sort of thing, right? That if you take the dot product of two vectors and you look at the magnitude, the absolute value of that, then it's controlled by the product of the magnitudes. Okay, that's what the Cauchy-Schwartz inequality says. There's more to it than that, but in any case, this is the main part of the Cauchy-Schwartz inequality. And I don't know how you proved it, but one way in Euclidean space, in Rn, is to make a geometric observation. So you make this sort of geometric observation that the dot product actually has a geometric meaning. It is the product of the magnitudes times the cosine of the angle between them, right? I don't know if you saw this, but you should have seen this, right? That you have two vectors, and then the dot product actually means the product of the magnitudes times the cosine of the angle between them. In that case, when you take the absolute value of this, well, right, the absolute value of this equals the absolute value of this, which is smaller than the product of the magnitudes times 1, right? Because the cosine, the absolute value of the cosine is less than or equal to 1, right? So, if I take the absolute value of this and then replace this by 1, it just gets bigger, right? And so that gives you the Cauchy-Schwartz inequality, at least in 2 dimensions. Okay. And to show this thing, you need to use like the law of cosines or something like that. Okay. You need to use the law of cosines. Okay. So that is what you may have seen before as the Cauchy-Schwartz inequality. We're going to give the complex version of that. We cannot prove it as geometrically. Probably when you're in linear algebra, you saw that, I don't know, you may have seen in linear algebra that in any inner product space, Cauchy-Schwartz inequality holds. So as long as you have an inner product, then you have a Cauchy-Schwartz inequality. So I don't know if you did that. That you can't do in this way. You can't do in this way because in an abstract inner product space, you're not talking about angles between vectors, right? But you have an inner product, and then you can still prove the Cauchy-Schwartz inequality from there. In any case, here's the Cauchy-Schwartz inequality for in the complex setting. So you have a a bunch of numbers, ai through an, b1 through bn, all complex numbers. And what it says is that if you take the sum of the AIs times the conjugates of the BIs squared, then that will be less than or equal to the sum of the AIs squared times the sum of the BIs, sum of the moduli of the BIs squared. Okay. You can see that this is basically the same sort of thing, right? Right. Over here, the dot product, right, is going to be VI WI, right? So you're taking the absolute value of the dot product, and then over here you've got the size. You've got the magnitude of V. So this thing is squared. You've got the magnitude of V times the magnitude of W, right? And all that is just the square of this. Okay, so it's just in the complex setting. And the dot product becomes this complex inner product where you take the vector against the conjugate of the vector. Okay, so here's the proof. So first off, without some notation, let A be summation of the AI squared, let B be summation of the BI squared, let C be summation AI conjugate BI. Okay. And so what we want to show, rewriting this, we want to show that the size of C squared is less than A times B. Right. So I'm just introducing some notation so that I don't have to write these things over and over. Okay. We want to show that. In other words, we want to show that AB minus modulus of C squared is non-negative. Okay. Okay, that's what we want to show. Without loss of generality, we may assume that B is positive. B is not zero. Right? Because if B is zero, that would mean that all the BIs are zero. Right? If the length of your vector is zero, you must be the zero vector. Right? So all the BIs would be zero. But in that case, what we were asked to show is that 0 is less than or equal to 0. We know 0 is less than or equal to 0. We don't need to worry about that. So without loss of generality, let's assume that B is bigger than 0, because otherwise it's trivial. Okay, so at this point, Rudin pulls out sort of a kooky move. He says, well, let's consider BAJ minus CBJ squared. Let's consider this from j equals 1 to n. Okay, so this is kind of kooky thing, which I'm not gonna try and explain it now. Okay, but it actually is related to the abstract proof in the general inner product space in linear algebra. So this is actually, it's basically doing exactly that thing. Okay. In any case, Rudin pulls this thing out. He says, well, let's consider this thing. Okay. And let's observe that it's positive, right? Because it's just a sum of positive numbers. Okay, it's just sum of positive numbers. And let's write it out. This is going to be summation. This is the same thing as summation BAJ minus CBJ. BAJ bar minus CBJ bar. Right? Because B and C, B and Nope. 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 You need a bar there. Right. B is a positive. B is a real number. So we, right? It should be. Okay, let me see this. It should be this, right? This times its modulus, right? In order to get the modulus. This times its conjugate in order to get the modulus squared, right? But we can put this down on things, right? We can write it like this, and then we notice that B is a real number, so we don't have to worry about it. Modulus of real number is just a real number. Okay. So then we write it out, right? Write out. Just do the calculation. We say, okay, this is going to be B squared summation AJ absolute value of AJ squared minus B times C bar summation BJ conjugate, right? So that's these guys. We need these guys minus C bar CB summation BJ AJ, and then plus CC bar summation BJ. Right. Okay, so that's just just multiply everything out. Just multiply everything out. Okay. Now this thing here is C, right? This thing is C. This thing here is C bar. Right. So and this thing here is A. Right. So we get B squared A minus B C bar times C, which is just C modulus squared, minus C modulus squared times B, so B times C modulus squared, plus C modulus squared times B. Right? Just notation. These things cross off, right? And we get B times BA minus C modulus of C squared. Right? We're left with this thing here. I factor out a B, I get B times AB minus modulus of C squared. Right? Okay. So but B was so what we get is that this thing is positive, right? This thing is bigger than or equal to 0. But B was bigger than 0, so we can divide both sides by B and not affect the inequality. And so we get that this thing is positive, which is what we wanted. So that's proof there. Okay. 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 Questions? Your real question should be, where did that come from? Where did that come from? Okay. It actually turns out to be the following, that it's sort of like this observation. The Cauchy-Schwartz inequality turns into the following observation, that if you have a vector B and a vector A, it's kind of funny, but if you take the projection of A on B and then subtract that off from A, you get this thing, A minus the projection of A on B, right? So you get this thing. And the Cauchy-Schwartz inequality actually corresponds to this thing being greater than or equal to 0. Okay, and that's basically what's going on there. This is the if you work it out, it'll be like basically the vector minus its projection. But I don't want to explain all that at this point. Okay. I guess that's a good place to stop. We'll just stop there. Okay. So yeah. Maybe I'll ask. So please read the section on Euclidean space. I think I'm not going to go over the section on Euclidean space. Let's go into chapter 2 next time. Okay, because I think the section on Euclidean space is pretty straightforward. It doesn't have anything kooky. So read that, and then we'll go into chapter 2 next time. Chapter 2 is where we introduce the new vocabulary of point set topology, the vocabulary that's necessary to show all those things in calculus that were left mysterious. Okay. So all what we've done here is just introduce the numbers, the world in which we're going to work. Next we're going to introduce the vocabulary that within that world will allow us to answer all the questions that were left unanswered in calculus. Okay, that's it for today.